In this work, we propose a simple and effective learning framework for generative models which contain latent variables. I am Sam Subakan, and this is joint work with Maxime Gas and Laurent Charlin, and we are part of MILA Quebec AI Institute. In generative modeling, the goal is to be able to learn distributions of complex real-life data. The examples might include handwritten digits, human faces, speech, or text. Let us start by introducing the main ideas behind the two-step learning framework that we propose in this work. Generative models typically consist of two components. First, there is an autoencoder, or just a decoder in GANs, and second, there's a distribution on the latent space. These two components are typically jointly optimized during training generally in the approaches in the literature. Whereas what we propose in this paper is to decouple the learning of the autoencoder from the learning of the distribution on the latent space. That is, we first train the autoencoder, we fix it, we obtain the representations given by it, and then we basically fit a distribution on these embeddings. Why do we do this? Because as we will show with several case studies, this way of learning the model enables sophisticated modeling combinations while it requires minimal engineering effort. So basically, showing this with several showcases is the main contribution of this paper. We also show that on several case studies that two-step learning performs comparable or even better than joint training in some case studies. We also propose a theoretical argument that asymptotically this way of learning the model converges to the true data distribution. So as to give an overview of the case studies, let me talk briefly about them. So the first case study that we will start the presentation with is changing the prior of a variational autoencoder. The goal of this is twofold. First, we show the need for a more complicated prior, and secondly, we demonstrate the engineering requirement differences between two-step training and joint training. Later on, we continue with HMMVE and RNNVE, which shows that just by changing the function you use to learn the prior distribution, with two-step learning, you can very easily learn distributions over time series. Later on, we continue with PCA GMM, which showcases that with two-step learning, since the learning of the autoencoder is decoupled from the learning of the latent of the distribution on the latent variables, we can incorporate learning algorithms which give globally optimal solutions, such as the PCA algorithm. And then we finalize the discussion with a case where we learn again in the latent space of an autoencoder. Note that in the last two cases that I just talked about, the joint training is not even obvious how to do, but with two-step learning, you can easily attack these cases. Let us showcase the usefulness of this approach by in a case study where we change the prior of a variational autoencoder. So basically, a variational autoencoder model is an autoencoder, non-surprisingly, with a regularized latent space. Namely, it is an autoencoder. In the first paper, it's basically in the first variational autoencoder paper. It's basically an autoencoder where we impose a Gaussian distribution at the output of the encoder. As I alluded to before, basically the way you train this model is by joint training objective, which consists of a reconstruction term, which minimizes the deviation between the inputs and the output of the autoencoder. So basically, we try to reconstruct these data items with minimal error as possible, and we have a regularization term, which ensures that the output of the encoder follows pre-specified prior distribution. In this case, it happens to be a spherical Gaussian distribution. But in the next 2 slides, basically, I will argue that this standard Gaussian prior is too restrictive, and we are basically better off with using a more complicated prior distributions for more accurate modeling of the data. To demonstrate the need for a more complicated prior in a variational autoencoder model, let us consider the following toy example. Let us have an observed space, observed data, where the data comes from a mixture of 2 Gaussians. We are in 2 dimensions, right? And we have 2 Gaussians, and we want to be able to learn the distribution of this. Basically, if we fit an autoencoder, if we fit more specifically a variational autoencoder, this is what we get in the latent space. So the output of the encoder, also that is the embeddings, are shown with the triangles here, and the PDF of the Gaussian distribution is shown by the yellow circle. And as we can see that after training until convergence, we see that the model is not able to contain, so to speak, the embeddings within the yellow circle. So we basically see that there's a mismatch between the imposed prior distribution and the output of the embeddings. And because of this, basically the generated data doesn't follow the actual observed data. And consequently, we see that we have a lot of red crosses, which are the generated data, which are not supposed to be here, basically. But there's a very easy fix to this. Like, basically, if we can somehow match this prior distribution and the output of the embeddings, we can get much better generation performance. And as we can kind of see here, we have like a mixture of Gaussian, basically like 2 masses where there's substantial probability mass. And one way to model this is with a Gaussian mixture model. And so basically, if we learn the Gaussian mixture model at the output of the embeddings, we see that the generated data is much better. We have much less spurious data that occur in the generated space. Okay. And basically, like this model, the fact that GMM incorporating a GMM prior is a good idea has been explored in the literature in various papers. But the problem with this approach is it requires substantial, effort to implement this model. We basically, first of all, we need to come up with an architecture which enables to be able to drive a joint training objective. And once we drive it, basically we need to code it. And basically in Python, this is what you get in terms of this is what you need to do to implement such a joint training objective. Okay. Whereas with the 2-step learning approach that we are proposing, what you do is you basically call your routine to train your VAE. You get your embeddings at the output of your encoder, and you basically fit a Gaussian mixture model on the embeddings. And basically, once you do this fix, you, as I've shown previously, you get much better generation performance. And at this point, you might be wondering what is the performance difference between GMM VE trained with 2-step and joint training. So basically, we compare the performance in terms of fresh inception distance on MNIST and Celebi, as we will show in the next slide. So we see that although the performance of the joint training is a little bit better than that of 2-step training, we see that the difference between these 2 approaches is actually much smaller when we compare the performance improvement we get with 2-step training when we incorporate the Gaussian prior. We observe the same behavior on Celebi also. The joint training is a little bit better, but because of the added flexibility of the two-step training, we can actually increase the complexity of the prior with two-step training, and as you can see with the green curve, we actually match the performance of two-step training. This framework, actually, the point of this work is to basically show that you can attack very complicated modeling, basically modeling challenges with this approach. Okay, for instance, if we want to model a time series with this approach, you can. Basically, it's like what you need to do is you just change the learning routine for the GMM with an HMM, and there you go. You can model complicated sound signals, for instance. So in this case, basically what we do is we learn an autoencoder on chunks of audio, and then we basically learn the transitions on how to transition between these chunks by basically fitting a HMM on the embeddings. Okay, and here's what you get if you train this model on some speech and some violin sound. And similar to the HMM case, if you want to incorporate an RNN to, for instance, learn a distribution between image patches, we can very easily do that. We implemented that on patches on the Celebay dataset, and as we can see, we are able to capture the distribution of human faces. So far, we have been talking about changing the prior distribution with two-step learning, but we can also very easily change the autoencoder with this approach. For instance, here we have a dataset of aligned brain images. So the goal is to be able to learn an autoencoder with a GMM prior, so as to learn the overall distribution of the images. So if you use a CNN autoencoder, the drawback that is known in the literature is that the maximum likelihood based autoencoders usually results in soft reconstructions. To alleviate this issue, what we can do is to basically incorporate a PCA autoencoder. So basically, the two-step learning approach enables us to incorporate the PCA autoencoder in the framework, and as we can see, we can get very sharp reconstructions with this approach, and therefore the generated data is also very sharp looking and very detailed. Finally, we can also incorporate in the final example that we consider basically incorporating GANs in the latent space of an autoencoder, and as we can see, the generation performance improves significantly when we do this. One thing to note about this example is that as with the PCA case before, the joint training objective is not straightforward, not obvious to derive, but the two-step learning approach enables us to perform learning in these cases. So as to conclude, let me say that the two-step learning is much easier to code. It's less bug-prone and more stable. We basically simply reuse existing routines to come up with new autoencoder and prior distribution combinations. And as we have seen in the GMM-VAE case, as the autoencoder and the learning of the prior distribution is decoupled, the training is very stable. And also we would like to point out that in the literature, in several works, people have seen that this approach works. But what we do in this work is to basically cast it as a general framework. And as we have shown in the GMM-VAE example, the performance is better or comparable than that of the joint training. And we have also posited a theoretical argument which suggests that the method recovers the true distribution in the asymptotical region. Thank you very much for listening, and you can find our code on GitHub. Thanks.